Hi, this is Keely, and let's talk about the charging time of a capacitor and how that affects the circuit. So we got a 15-volt battery connected to a 15 kilo ohm resistor and a 1000 microfarad capacitor, all in series with each other. And we want to figure out what happens. So when this circuit is first turned on, let's think about it like this. This is the positive side of the battery, and that's the negative side. So if we follow the conventional definition of current, that's the flow of positive charge. Positive charges leave the battery, go through here, and they'll start building up on this side of the plate of the capacitor, but this side will build up an equal negative charge. Well, think about it like this. This positive charge comes around, positive charge builds up here. The positive charge on this plate wants to get away from this positive charge because of law of charge, opposites attract, likes repel. So that positive charge continues through here, and then goes to this side of the battery because it wants to get over here. Well, as this plate builds up charge, what happens is it gets more and more difficult for charge to leave this battery and move over here because these positive charges don't like each other either. And so it's more difficult for those positive charges to build up on that plate. And thus it's harder for these positive charges to make from this plate to make it all the way around to the other side of the battery. And so the whole amount of current in this circuit diminishes over time. It looks something like this. So when it's first turned on, we get the maximum amount of current as if that capacitor wasn't even there. But as time goes on, it quickly drops off. If I can draw this the way I want, eventually the current will drop down to zero. By that same token, the charge on the capacitor will build as a kind of reflection of that and get more and more until after a certain time the capacitor is fully charged. We want to know how long does this take. Well, we have something known as a time constant with capacitors. And your time constant, which we use the Greek letter tau for, is simply the resistance times the capacitance. And so for this circuit, it'll be the 15,000 ohm resistor times the 1,000 microfarad capacitor. And if we do that, we get 15,000 times 1,000 times 10 to the negative 6. We get 15 seconds. And so this tau is 15 seconds. So after about 5 of those time constants, in other words, 75 seconds, that capacitor should be completely charged. And when it's completely charged, no current can flow through the circuit anymore. So let's do a problem with one of these and actually calculate some of these values and times for a specific circuit. Matter of fact, this one right here. Here's our circuit again. Same resistor, same capacitor. And I want to figure out the current going through the circuit when it's first turned on. So the equation that goes into that one looks like Ohm's law, as well as the charge on capacitor, because where that comes from is C equals Q over V. And we just rearrange to find the potential difference. And that's where that term comes from. It comes from this. So the voltage from the current and the voltage from the capacitor should add up to be equal to the total voltage from the battery, which in this case is 1.5 volts. So when it's first turned on, there is no charge built up on the capacitor. So this term is essentially zero. So we just have Ohm's law. V equals IR. Voltage is 1.5. Current we don't know. Resistance is 15,000 ohms. So the current, when it's first turned on, will be 1.5 divided by 15,000, which is 0.0001 amps. What about if the circuit is on for a long time? Well, we use the phrasing long time. That means that the capacitor is completely charged by then. So if the capacitor is completely charged, then all that voltage is in the capacitor, so there's no current. So when it's completely charged, the current is 0. No amps flowing through that circuit. So we need to know what is a long time for this circuit. Well, tau is resistance times capacitor, or capacitance. So 15,000 times 1,000 times 10 to the minus 6. And we did that earlier, that's about 15 seconds. So for it to be a long time, then that is 5 times tau, which in this case is 5 times 15, or 75 seconds. So after 75 seconds, that capacitor should be completely charged. Well, what if we just wanted the capacitor to be charged to half the voltage of the battery? How long will that take? Well, that's where we have this equation here. The voltage on the capacitor is equal to the voltage of the battery times this quantity, 1 minus e to the minus t over RC. So that's tau. So sometimes that's written as minus t over tau. I'm going to leave it like this. And so we've got to solve this for t if we're at half the voltage of the battery. So half the voltage of that's going to be 0.75. Voltage from the battery is 1.5. E to the minus t in RC, well, is 15 seconds. And so I'm going to go ahead and divide the 1.5 to both sides. So when I do that, we get 0.5 equals 1 minus e minus t over 15. Remember that 15 is r times c. Move the 1 over, so I get minus 0.5 equals minus e minus t over 15. Negative signs go away. But I've got this e expression. So we need to get rid of that. So we're going to use the natural log. The natural log of 0.5. The natural log and e cancel each other out. And so we just get minus t over 15. Now here's another little trick that I like, because if we do this, it looks like we're going to get negative time. And you can't really get negative time. That doesn't make sense. But there is a property of natural logs that looks something like this. Natural log of a number is equal to negative the natural log of that number inverted. So 0.5 is the same thing as 1/2. So I'm going to invert that. So we get negative natural log of 2, when I flip it, equals negative t over 15. Well, now the negative signs cancel out again. And so I get 15 natural log of 2 equals the time. So take the natural log of 2 times 15, and I get that the time for this circuit, for that capacitor to reach half the voltage of the battery, is 4 seconds. Now to leave that with some variables in it, it looks like this. Because remember, 15 is really r times c. So the natural log of 2 RC is equal to the time for half the voltage. Now, what if you're not going to do half the voltage? Well, you can do whatever voltage you want. Just remember that you can take the inverse of whatever is here in that to get rid of the negative signs. So if you want a quarter of the voltage, natural log of a quarter will be negative natural log of 4. And then solve for time. Now, what if I want to figure out the charge on that capacitor at that moment? Charge is equal to CV 1 minus e to the negative t over RC again. And we can solve for the same thing. This will be the maximum charge possible because, again, C is equal to Q over V. Solving that, we get Q equals CV. So that's the maximum charge that it can hold. So the charge on that is equal to the maximum charge, 1 minus e to the negative t over RC. And we can solve for that to figure out the charge on the plate at that time. Thanks for watching. Tune in for more physics and hopefully like and subscribe to the channel. Goodbye.